Okay, so the very last thing was the tax rate, and we have found the formula. We have found the diagram of how computed, and we have found a formula for it. This is the presentation. The standard way to present is algebraic, and the algebraic is here so that you can always see the formula. The disadvantage over the diagram is that the conditions follow the formula. Okay, so rather than vice versa. So the diagram, there's a fork in the road, and there's like a sign with arrows pointing in which direction you go, depending on what's that you've got. So you check out your wallet or whatever how much you got of the money you have received, and then based on that, it tells you in which of the three roads on that fork you take. Okay, so that's the logical way of doing things. It's slightly less logical, but that's the standard way. It's at the bottom. It is a formula, and the conditions are followed. You have to read it from right to left, pretty much. Okay, so f of x is the input, and then you take it and you sort of and you check it out like here. So whatever number comes as an input, you have to verify which one of the three conditions are satisfied. So you can think of it as a fork. You can think of it as like a door on which tells you which door to take. Okay. The issue that came up at the last moment is that this is not a formula that you can use to actually compute your rate, because nor actual tax bill, because it gives you only the marginal tax rate. So you put your money in the three brackets. You split your money between the three brackets, and then to each of those parts will be subject to that rate. Okay, so the first 10,000 you pay nothing of. Whatever between the amount that you receive that lies between 10,000 and 20,000 is taxed under 10%, and the rest is taxed under 20%. Okay, so like I said, split into three. The graph, it actually helps probably if we plot the graph of this function first and then compare it to the tax rate, the tax. So this is the tax rate, the function f, y equal f of x, and there are three pieces will be visible, 10,000, 20,000, where things change. So x is your input, income, which is also an input. And this is the rate right here. That's y. Okay. So so as you can see, there is no change in the value of y, or within either of the all of the three of the intervals or pieces. So these are the pieces. That's why it's called piecewise defined. Okay. So if I take the 0 here, this is the piece of the graph that I'm talking about. So it includes the endpoint, both of the endpoints. So income 0, the tax is 0, and all the way to 10,000. Even if you have exactly 10,000, the tax rate is still 0. Okay. On the y-axis, I'll put here 10 percentage-wise, or 0.1, 0.1 and 0.2, the rates. And then I progress to the second value of 10% of 0.1, if you prefer. Once again, it's a constant, which means that that part of the graph will be constant, except if you got to be careful, so you don't just draw a line, but you also take care of the endpoints, include or not to include. Since you remember, we need to satisfy the vertical line test. So if you worry about the vertical line test, you're going to end up, these are the vertical lines that might get you in trouble. So you have to have one output for each input. Okay. So then 10,000 is taken. Okay. So that orange dot over here is taking care of the 10,000 income. The tax rate is 0. Okay. So which means that I have to have a circle here. No point. So it's a point with excluded. It is a straight line with excluded endpoint. Elsewhere, you might see this kind of notation with arrows, meaning the same exact thing. So the endpoint is excluded. But on the other end, the point is excluded. As you can see, this is why. So when you have 20,000 income total, the rate is 20%, 10%. Okay. So by the same logic, I move on to the next one, and to 20, and this is starts with a hole, and then this line does not have an end. Presumably, no matter how large the income is, it is taxed under 20%. Okay, so that's the graph of my rate function, or marginal rate function. If I want to actually figure out the way how much I'm supposed to pay, I try to describe it, but without having an actual formula. So X is still income. And I don't want to come up with a formula because it's a bit lengthy, but I will plot the graph. Okay? So how much do I pay? The x-axis is divided into the same pieces just as before, 10,000, 20,000. That's where things change. But within each of these three pieces, there is no change. Okay? So originally I'm still paying nothing. So this is my tax bill. And originally I'm paying nothing. It's still zero. But then as I progress from 10,000 on, so imagine that you would get getting more and more pay every year. You're getting paid more and more. So up until 10,000, you're not paying any taxes. And then you pass the threshold of 10,000, you start paying 10 cents per each dollar that you get. So what does the graph look like? Let's say, let's take 1 point. If I'm being paid 20,000, I'm paying 10%. Okay, so I'm going to put it right here. So this is 10%, which is 2,000. So this will be 2,000. Oops, that's 20. 2,000. So if you don't want to do all the work at once, you know that you're gonna you just do a few times. So at 20,000, I'm paying 2,000, right? 10% of 20,000 is 2,000. That's my tax rate. So the question remains, how do I get from that curve over there to that one? And the answer is by straight line. So like I said, this is a proportion. If we're talking about rates, we are paying proportion of your income. Okay, so and that's literally what it means. So everything above 10,000. So whatever happens to the left of 10,000 doesn't matter. So you take your amount, subtract 10,000, and each of those, and on each dollar that you have there, you pay 10 cents. Okay? And as you can see, you pay more and more. Okay? So can you guess what happens beyond 20,000? Yeah. Yeah. So what does the graph look like?
It's going to go up.
Up, but it's still up. What's the difference? What? It will be steeper, right? It will be twice as steep like this, roughly. So still straight line, but steeper. So in other words, those numbers that we have in the first graph are the slopes of the graphs of the graph that followed. So 0.1 slope, 0 slope, 0.1 slope, 0.2 slope. That's what we have here. And then we made up a function that is on purpose. So it is linked into one curve. So we call those functions continuous, but that will have to wait until calculus. It's also increasing, an increasing function in the sense that as your income increases, your tax increases too. So this is all by design. So the formula you can take as an exercise and try to come up with a formula for this kind of income. The graph is there, so all we have to do is just to find the formula. It will have the same. So this part will be the same. This part will be the same, or this part will be the same. But the actual formulas will be different because they are They are not constant, so not just numbers, but a constant. So some linear function. Every function in that list will be a linear function, and they're linked up into one curve, which is important, so that if you why there are no gaps. So not only it is increasing, it does not increase in increments. It increases continuously in the sense that if your income grows by a little bit, then there is no dramatic change in your tax bill. At least that's the idea. Okay, so this is more complex than the idea deserves in a way. I mean, it explains why we care, but there are simple examples of piecewise defined functions that are actually very prominent in the rest of the mathematics, and these are the two. Number one is the sine function, and the second one is the absolute value. So the sine function stands for SIGN. So it gives you, thus literally, almost literally, gives the sine of the input, x that is. So roughly speaking, the sine of -3 is -1, the sine of 0 is equal to 0, and the sine of 5 is equal to 1. Okay, so we strip the number of its magnitude and only look at its sign. That's why it's called the sine function. Okay, so the idea is clear, I hope. But now we have to come up with, let's come up with the diagram, the formula, and the graph of this function. Okay, so x comes in. There are how many possibilities? 3 possibilities, yes. So what are the possibilities? It is determined by the sign of x. So those are the 3 possibilities. What are the possibilities?
-1, 0, and 1.
No, that's not what I'm. No, those will be the outputs.
Oh.
Okay, so you ask a question first, and then based on that, on the answer to that question, you take the right fork, and then the output, as you said, will be indeed -1, 0, and 1. So, but what are the questions? So these are the answers. What are the questions?
-3, 0, and 5.
Well, I meant this only as an example rather than the whole thing, because any number should be able, the domain should be everything. Okay, so domain is negative infinity, infinity. Okay, so any number should come in, and then sine of -5 is -1. No matter what negative number is, the output is -1. Okay, so that's the answer to the first question. So the question is x less than 0? So that's the sign, the arrow that points you, depending on your input, it tells you which road to take, and you take that road if x is less than 0, and then the answer is choose -1 to be your output. Okay, and then the second question is x equal to 0. So if yes, then you discard x. You don't need x anymore because x only tells you which road to take. You choose 0, and the outcome is y. That's your output. Okay, and the third possibility, x is positive or not, and then you choose 1 in that case. And that is y, and then you merge these together, and then you have your output roughly. That's what it works, how it operates. So once again, you're choosing a number based on what x is, but that is literally a choice. You don't need x for computation. Okay, so that just like with rates, just like with income rates, income tax rates. If you know your income, it only tells you which of the doors to take, and then the answer is behind that door. But you don't need x. Okay, so the formula now, algebraic formula, sine x is as I suggested, read it from right to left. So these three conditions that are in the beginning will be at the end. So if, and those restrictions to be, conditions to be verified, x less than 0, x equal to 0, x larger than 0, and then I just those three numbers I put in the same order, -1, 0, and 1. Okay, so that's the formula. Piecewise defined. So once you have the formula, either one of the two, you can have a bunch of x's and y's, and you just have enough data to plot the graph. -1, -1, -1, 0, 1, 1, 1. Okay, that's what the values look like. So if I now plot, if I just plot these points, they behave very simply. So, okay. -3, -2, -1, 0, 1, 2, 3. Okay, so I'm plotting these points. So one on the same level at -1. Okay, -1. And then next one is on the level of 1. In the middle we have 0. Okay, so these are the only points that we have in our table. So that's why I only plotted those 7 points. But that's not enough. Even though some parts are kind of predictable, these parts are predictable. I will connect the 2 consecutive points into by a straight line. But what's happening in the middle is slightly more complicated because there are no values between taken. There are no y's between 1 and 0, as well as 0 and -1, because the range is, what's the range? No. Look at the diagram. Range is all possible values. Actually, the values that actually have been taken by the function, if you look at it. What are the possible values of the output? So this is y. Well, the values are listed for you. There's a list. You cannot have value of 10. Why? Because you can only choose between the 3, -1, 0, and 1. These are the only values in the range. The actual values for which there are x's. So you cannot find x for 10. You cannot find x for 0.5, anything like that. Only these 3 are in the range. So it is -1, 0, and 1. That's the range. So once that is established, then your graph, then you start thinking better about the graph, because it appears to be. Remember how we think about ranges in terms of the graph. It is as if you take your graph and shrink it. You put it on a piece of paper or a piece of rubber maybe, and shrink it towards the y-axis. So and then that whatever your graph becomes the range. Okay, so how do you shrink it in such a way that you end up with nothing but 3 points? It means that there are 2 horizontal lines and 1 point in the middle. That's it. There is nothing else. Okay, so you are not allowed to have graphs. So no graph here and no graph here, or no graph there, because there are no values of y. In fact, I'm going to plot the range. This is the range. No, maybe better color, better choice of color maybe. This is the range. Only 3 values. Remember, range is the y's. So if I want to visualize them, I put them on the y-axis, just as I would visualize the domain on the x-axis. And these are the only three values, -1, 0, and 1, that I can see on the y-axis. And once again, if you take a strip of the graph between those two, or above or below, there can be nothing there. So the conclusion then is that this is the only way we can finish the graph. Straight line here, straight line there, as well as one single point at the origin. That's all. That's the whole graph. Okay, so if you want to now all this analysis to put together, the graph is very small. So like this. Okay, so that's the whole graph. Okay, so the 1 and -1. So any questions about this? Okay, so let's move on to a function that you may have seen before, and that is the sine, the absolute value. What does the absolute value do?
It makes everything positive.
It makes,
Or like it tells how far away it is from 0, comma.
right, yeah, okay, let me write it down. The distance from x to the origin. Okay? So that is a geometric explanation. So we have on the x-axis, so if this is 5, then the distance is 5. If this is -5, the distance is still 5. To the left or to the right? So that, in that sense, we make everything positive. The way I just talked about, it is the opposite of what the sine function does. The sine function strips the value of x of its magnitude, and this one is the opposite. It concentrates on the magnitude and strips it off of the sign. So it doesn't matter on which side of the origin that number lies; it will produce the same number. So the opposite of the sine function, which tells you exactly to the left or to the right and nothing else. Okay, so that's a way to remember it, but that's not the something to be done with computationally. So let me write a few. Once again, x of 5 is equal to 5. Absolute value of -5 is 5. Absolute value of 0 is 0. Just a few examples of what absolute value does. Okay, and the distance idea will come up later. Okay, so now I want to have a diagram of how we're going to compute this function. Okay, so x is the input. How many we got to have a fork? How many roads or doors? So you have x. You know the idea of how the absolute value of x is computed. Now you have to present an algorithm or a list of steps so that everybody else can do it too, without an explanation. So a computer could do. So how do you teach a computer to compute this function? Variables. X is the variable. So the computation is different. Well, let's take the simplest case. Let's take the simplest case. What if x is positive? Then what is the absolute value? X is positive. Then what is absolute value of x? X. Okay. If x is 0, then absolute value of x is 0. X is negative. What's the absolute value of x?
Okay.
No. What?
Positive x.
What's positive x? How do you make a negative positive? That's the way to answer the question. You have a negative number x. You want to make it positive. How do you make it positive? Multiply by -1. So it's negative x. There we go. So we have here pretty much everything is taken care of. The three cases are right there. They cover everything. All possible inputs are covered, and we know what to do in each case. So you can just stop here and say this is the list of instructions. I'll just quickly take it and put it in the form of a flow chart, which is not a big deal. So I have three questions to be asked. X less than 0. I put them in the order, the same order as for the sine function, and three questions being asked. In where x is relative to the 0, and then depending on which door you take, then you do have to do a computation, unlike in the last question. So if it is less than 0, multiply by -1. Okay, so that's the step, and the whatever comes out is your output. If x is equal to 0, just choose 0. Okay, that's easy. And then in the third case, what do? You just pass it. You don't do anything. And that's your output. Okay, so that's the same thing, a more like computer programming type oriented way to present things. So boxes, questions that take you in different directions, and then the output y. Okay, but like I said, this is the whole story is here, and also we can take it and just do as we did. Let's write the formula, the piecewise defined formula. Well, actually, before I do that, I can point out that you can make your life slightly easier if you just you could hypothetically reduce the number of cases to 2. You can combine these together, or you can combine those together. Either way, the computation will be the same. So either in case of x equals 0 can be included in either case 1 or case 3. So either way, you multiply 0 by -1, you still have 0, or you do nothing in case 3. So it's a possibility, even though not that important. You can just as well keep the previous definition. Okay, let me write the formula. So f of absolute value of x is so in the opposite order. So conditions second, and conclusions and operations next. So negative x if x is less than 0, 0 if x is 0, and x if x is larger than 0, like this. So that's the piecewise defined formula for the function. Okay, so plotting once again. Okay, let me have a table first. So once again, I have a few values of x and y, and so once again, -3, -2, -1, 0, 1, 2, 3. Once you have this diagram, it's no trouble to carry out this computation. In fact, as you move along, you know that you will be using one formula for a while, then once you use the middle formula, and then after that you're using the third formula. So I'm multiplying by -1. Okay, so carefully, since I'm still negative, well, let me maybe divide this into 3 parts like this. These are the 3 conditions, 1, 2, and 3, and the different formula applies to these 3 separately. Okay, so the first 3, even though there aren't many of them, I multiply now by -1, so -3 times -1 is equal to 3. -2 times -1 is 2. -1 times -1 is 1. So that's how a computer would do it, even though you are certainly welcome to to remember that the absolute value of -5 is 5. So you drop negative sign, but that is tricky. So there might be trouble with this approach of dropping -1. What is the absolute value of negative x? Careful. The absolute value of negative x, what is it? No, because what if x is negative? If x is negative, then it's not working out, right? Because absolute value has got to be positive. So it's not x, but what? Anybody want to guess? Well, it's the same as 5 or negative 5 give you the same number. So the absolute value of 5 or negative 5 is the same. So the answer is absolute value of x. Okay, so yeah, just in case. It's not really that you might need it. It's just a warning about thinking too simply about the absolute value. Thinking about the absolute value as dropping negative sign, which is okay whenever you deal with specific numbers. And you know that you drop negative from negative 5 and you end up with positive number, everything is fine. But if you're dealing with variables such as x, then dropping negative sign might produce a negative number because you don't know what x is. Okay, so just be careful. Remember that that's algorithm is here on purpose, that you just multiply by negative 1 if the number is negative. Otherwise, you can think of this as a simplification. So negative sign inside of the absolute value doesn't do anything. So you can just drop it. Okay. So now I'm doing the same thing with 0. There is nothing to do. You just choose 0. And then I do nothing but pass along the positive values, 1, 2, and 3. Okay, so these are my 7 values again. The pattern will become clear once I plot them. You can probably already see the pattern of how I go 3, 2, 1, 0, 1, 2, 3. Okay, so even before plotting, you can just looking at the data, at the numbers, you can tell what it's going to look like roughly. So what does it look like? Negative 3, 3, negative 2, 2, negative 1, 1, 0, 0, 1, 1, 2, 2, 3, 3. It is a V shape, yes. It's often described that way. Okay, so and then that logically you try to connect two consecutive points in a manner that is the most natural, and it turns out that the most natural way is to connect them by straight lines. We know for sure that they are straight lines because if I take more values, I take 1.5, what's the absolute value of 1.5? It once again is 1.5, so it is definitely, if we ignore all the negative values of x, we have a straight line. We have a straight line y equal x. So this part is y equal x, a straight line, and this one y is equal negative x. Also a straight line, but with the slope, with the negative slope. Okay, so okay, so you can see let's ask ourselves the usual questions. I already did not, but probably should have started with the saying that what the domain is. Well, it is easy to overlook when the domain is everything, so no trouble that can possibly arise here. What is the range?
Is everything as well?
No. Once again, look at the positive values. You can look at the second.
On every positive number?
Every positive and 0, yes. So it's a 0 infinity. So either you look at the at your data on the right. So you have two columns, and roughly speaking, the first column will give you the domain, and the second will give you the range. Okay, you cannot have negative numbers in the second column because that's the absolute value. So the range then will be everything other than negative numbers. You can also see them from the graph. So imagine once again on a piece of fabric, you have the shape, and then you shrink it. So then you have a bunch of all the points will land on the above the x-axis, on the y-axis, but above the origin, and there will be nothing below because you're doing it like this. So let me maybe do it once. That operation, so this is what I'm talking about is like this, pushing everything gently towards the whole thing is shrunk towards everything is shrunk towards the y-axis. Okay, so the x-axis then becomes a point, and then this is what I end up with, like this. Okay, so this is the origin. Okay, so yeah, so because the range lies in the y-axis, so we take the graph and see if anything is left of it if we just concentrate on y-axis it how. Okay, so any other things that you want to say about this function? If you take a closer look at the graph, what we talked about last week, what's so special about this graph?
It has a mirror.
It has a mirror symmetry, right? Mirror symmetry over the y-axis. Shortly we'll talk about these functions. They are called even functions. And so it is similar to, well, y even. Remember that x squared is an x fourth and x sixth. All even functions. They have this mirror symmetry with respect to the y-axis. And this one, the absolute values has the exact same symmetry. Okay, so that is a piecewise defined function. Also very important. Probably be more important than the last one. The next one is also important for different purposes. Slightly more challenging though. It's called the integer value function. So the idea, it's like a rounding up function. Okay, so the notation is brackets. So say 1.3 is equal to 1. 2.9 is equal to 2. That's the function. So rounding up, or rather rounding down, more precisely. So the nearest integer, that is less than x. So the nearest integer below x. That's the definition. That's like a verbal definition. So to get do actual computation, you have to sort it out and then put it in a more precise form, as we just have been doing. So the idea is it is on the written in a fairly straight way. So it has got to be an integer, but it is not the nearest. As when you do rounding up, you could round up or you can round down, right? So for example, 2.9, you would round it up to 3, but this one is slightly simpler, so you always go down, never go up. Certainly worth mentioning that if you are already integer, then nothing happens. Okay. Okay, so let's ask ourselves the usual questions before we start computing. The domain is everything. What about the range? That's right, all integers. So you can, in fact, before you start computing, you can plot both of them just for extra experience. So this will be the domain on the x-axis, and then you plot the range on the y-axis, like this. Okay. So which means that so you plotted it. Okay. Now whenever time comes to plot it, the graph will lie somewhere here within these straight lines. like this. Okay, so it's not going to be anything similar to what we have seen because it will have to jump, just like the sine function will have to jump from one level to the next. And you can guess roughly it will be roughly like this, right? So as x grows, that integer value will also grow, but gradually. Okay, so well, let's just so we have the range and we have the domain. Let's do a few values in order to actually being able to plot it. So I'll have a few values of x and y, okay. And this time I'm not going to take any integers because, well, I'll take some integers, but I need a lot of non-integer values to actually show what's happening. Okay, so because that's where things are happening. As you can see, the fractional values are where the answer is unpredictable, or predictable but not obvious. So I'll start with negative. So say I'll start with how about negative 2, negative 2, negative 1.5, negative 1, negative 0.5, 0, 0.5, 1, 1.5, 1.5, and 2. Okay, so a little bit more values than usual. Okay, so I'm not going to have a formula, but we know what the answer is supposed to be. So what is the integer value of negative 2? Negative 2, okay. Of negative 1.5? No, you got to go down. No, down from 1.5. Negative 1.5 down is negative 2. From negative 1, you're not going anywhere. For negative 0.5, you're going to what? Down.
Negative 1.
Negative 1. Okay, 0, 0. I'm sorry, I skipped 1. I skipped 1, so 1, 1.5, 2, 1, 1, 2. Okay? Okay, so we'll just plot it. So we'll have like 9 points. We'll plot them. Okay? Okay, let me stretch it a little bit. Like this. Okay, negative 1, negative 1, negative 2, 1, 2, negative 1, negative 2, negative 1, 1, 2. Okay, so so these are just points. I have the coordinates lighten up, so negative 2 is here. And where's my next point? So I'm moving left, right, according to on the x-axis, 0.5 at a time. And then sometimes I make a jump, a whole 1 unit up, or alternatively I don't make any jump at all, and there's no change. So from 2, x moves to negative 1.5. What happens to y? Nothing. So this is where my second point is. On the same level, 1.5 to the right. Okay, so I'm moving to negative 1. Negative 1 is over here. Negative 0.5, negative 1. Once again, no jump. Staying on the same level. And finally, 0, 0. 0.5, 0. Okay. Once again, progressing little by little. So you already can guess what probably is going to happen. So the next one is 1, 1. 1.5, 1. And 2, right here. Okay, so so what does it look like? Stairs, right. So we just we certainly can connect these points. We can predict what's happening there. Well, nothing, but the value remains the same. We only need to know what's happening in these areas. to the right of 0.5. So if instead of, say, 1.5 over here, I take 1.7, 1.7 is still 1, right? 1.7 is still 1, so I'm staying on the same level. And on, no matter how close I'm going to get to 2, the answer will continue to be 1. Okay, so I'm drawing this line, and what do I put at the end? An open circle, right? Because, why? Because the value at 2 is 2. Okay, so it will be inclusive at the left hand of each of those steps. On the right, it will be a hole, like this. A hole. Okay, so as you can see, the vertical line test is satisfied because of those holes. So let me confirm that like this. So I drew those pink lines, and I'm making sure that there's exactly one point on the graph that lies above on that vertical line. Okay, so as you can see, even though it appears there are two, maybe the reality is only 1 point. Okay, so once again, it's a staircase, entirely horizontal. So the graph cannot have vertical parts, right? Because it's a graph of a function. So that's why there are gaps, and only the horizontal part of the staircase consists actually of the of the graph. Okay, so the questions that remain are. Let's see. Do you see any symmetries? Well, there are two main symmetries, so let's just check them out one by one. The mirror symmetry? No, right, because if you flip it like this, there will be different graph. The rotation, however, try to rotate it 180 degrees. What do you get? Well, the answer is no. It's not quite right, because if you just concentrate on the points around the origin, this part over here, then if you rotate this piece of the graph, it will be pointing to the left. Okay, so that's not symmetry. Okay. Okay, so I'll stop here and we'll continue tomorrow.